Good morning to all. My name is Roger Joseph. Today I'd like to speak something related to lanthanides. Lanthanides and actinides were considered as F block elements. Lanthanides belongs to the sixth period of the periodic table and actinides belongs to the seventh period of the periodic table. Lanthanides are those 14 elements from atomic number 58 to 71, and actinides are those 14 elements from atomic number 89 to 103. Electronic configuration of lanthanides, you can see that 6s2, 5d1, 4f1 to 14. Similarly, that of actinides is 7s2, 6d0 to 1, 5f1 to 14. That means in both these cases you can see that in the case of lanthanoids 4f orbital is filling, and in the case of actinoids 5f orbital is filling. In both these cases you can see that the pre-penultimate shell is occupying finally. The influence of this is very high because we know that the atomic radius is calculated on the basis of the distance from nucleus to valence electron. But in this case, the central electron, the last electron, pre-penultimate shell. What are the lanthanides and actinides series called? The lanthanides are an important group of elements. The elements of lanthanide series is also known as rare earth elements. Both lanthanides and actinides make up is known as inner transition elements. Every one of you know that D block elements were known as transition series, and lanthanides and actinides or the F block elements were known as inner transition series. When we look into this case, you can see that the pre-penultimate shell filling has very impact on oxidation state. When we consider the similarities, we know that in both these cases, the n-2 f orbital is filling, and the difference is lanthanides can show a maximum oxidation state of +4 or +5, but actinides are able to show oxidation states such as +3, +4, +5, +6, and +7. Instead of this, some of the lanthanides and actinides are also exhibiting oxidation states such as +1 and +2. That's a rare phenomenon. Every one of these elements does not exhibit that +2 or +1 oxidation state, but some elements are obviously exhibiting the +1 and +2 oxidation state. Let's see. When we consider the case of cerium to gadolinium, you can see that only gadolinium exhibiting +1 oxidation state, but all these elements are exhibiting +2 and +3 oxidation state. But you can see that cerium, praseodymium, neodymium exhibiting +4, and the praseodymium exhibit +5 oxidation state. This is the scenario in the case of early lanthanides. When we consider the next lanthanides, you can see that in the case of next lanthanides, that means lanthanides from atomic number 65 to 71. In this case also, you can see that the common oxidation state means the oxidation state exhibited by all elements is +2 and +3. But in this case also, terbium is another element which also exhibit +1 oxidation state, and terbium and dysprosium, both these elements are able to exhibit +4 oxidation state. But you can see that all other elements are exhibiting +2 and +3 oxidation state. This is about oxidation state. The main theme behind this oxidation state of lanthanides is the difference between 4f and 5d orbital is very large. Next is, what is meant by lanthanide contraction and what causes it? When we consider the case of lanthanide contraction arises due to the poor shielding effect of 4f electrons. Every one of you know that lanthanides are those elements from in between atomic number 57 to 71. What is lanthanide contraction and what causes it? Lanthanide contraction is greater than expected decrease in the ionic radii of elements in the lanthanide series from atomic number 57 to 71. This results in smaller than otherwise expected ionic radii for subsequent elements. Every one of you know that if we move from left to right, atomic radius steadily decreases. But in the case of lanthanides, that decreasing range is very high because of the 4f electrons are belongs to the pre-penultimate shell. In this case, we are considering the distance between nucleus and 6s electron is considered as the atomic radius. Due to poor shielding of this 4f electrons, the atomic radius steadily decreases from left to right. Consider the case of single electron systems such as hydrogen. This type of shielding is not present. The shielding capacity of various orbitals, you can see that yes, orbital electron belongs to s orbital has maximum shielding capacity, and electrons belongs to f orbital possess lowest shielding capacity. When we consider this effect, you can see that if 5d and 6s electrons are less shielded by the 4f electrons, that's why nucleus is able to attract effectively this 6s electrons towards it. That's why the atomic radius is steadily decreases in this case. That means in the case of lanthanides.
ഷീൽഡിംഗ് എഫക്റ്റിലുള്ള വ്യത്യാസം വളരെയധികം പ്രാധാന്യമർഹിക്കുന്ന ഒന്നാണ്. When we consider the case of multi-electron system, we know that the decrease in atomic radius brought about by an increase in nuclear charge partially offset of increase in the electrostatic repulsion among the electrons. But in the case of single electron systems, such electrostatic repulsion is not present in the case of single electronic system. In particular, the shielding effect operates the electrons are in the outer shells. When we look into the lanthanide contraction pattern, you can see that from atomic number 58 to 71, the atomic radius steadily decreases from 2.7 angstrom to 2.4 angstrom in the case of 70, and the case of 71 it is just 2.25 angstrom. This decrease is steady. You can see that this is only because of what? Only because of the poor shielding effect of f electrons. That means those electrons present in the pre-penultimate shell possess poor shielding. That is why the steady decrease in the electronic configuration. Let's compare the atomic radius between 57 to 72. You can see that in the case of 57, atomic radius is 2.74 angstrom. And in the case of atomic number 72, that means in the case of hafnium, you can see that the atomic radius is just 2.16 angstrom. And that steady decrease, 14 elements are present in between these two. You can see that the steady decrease arises only because of what? The steady decreases arises only because of the poor shielding effect or poor shielding capacity of the f electrons present. Then let's look into what are the consequences of lanthanide contraction. When we consider the consequences of lanthanide contraction, due to lanthanide contraction, separation of lanthanides is very, very difficult. And the basic strength of hydroxide are almost same. And another important class factor is the similarity between second and third transition series. That means 3D and 4D series. When we consider these cases, you can see that the electron, the atomic radius of 3D and 4D series, that means second and third transition series are almost same. Let's look into a comparison graph. When we look into this graph, you can see that from scandium to manganese, the atomic radius is steadily decreasing. Then it steadily increases from iron to zinc. When we look into the case of second and third transition series, you can see that the atomic radius pattern is overlapped or merged. This is only because of the influence of lanthanide contraction. When we look into the atomic radius of zirconium and hafnium, you can see that the atomic radius of these two elements are almost same, but in the case of beryllium and tantalum and tungsten and molybdenum, you can see that the atomic radius is almost same. The case of gold and silver, etc. This is mainly because of the lanthanide contraction. Thank you.